Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhiday Namdar, Senior College. Now, in groups and coding theory, we start with the last unit, that is coding theory. Now, see second point, decoding and error detection. Using the given MN encoding function E from Bm to Bn, we get a code that belongs to Bn. This encoded word E of B equal to X is received at the receiver's terminal when transmitted through the channel. Suppose the received word is denoted by xt. If x and xt are equal, the identification of the word sent is resolved and we get B belonging to Bm back. However, due to noisy channels of transmission, this is not always the case. In fact, receiving the correct code word is a very rare case in reality. In such situations, we face the problem of identifying the word B that was the original message. Now see what is decoding function, which decodes the code word. An onto function D from Bn to Bm is called an NM decoding function associated with an encoding function E from Bm to Bn. If D of xt equal to B dash is in Bm and is such that when the transmission channel has no noise, then B dash equal to B. That is, D composite is equal to identity function on Bm. Now the decoding function D must be an onto function so that every received word is decoded to give a word in Bm. See, the function is onto, it means every element in codomain must have pre-image in Bn. Now Bm contains all the words and that we have to decode it, and so the function must be onto function. The decoding function decodes properly received words correctly, but for words improperly received it may or may not be correct. Now next is maximum likelihood technique. Now this technique is used for determining a decoding function D from a given encoding function E. Given Mn encoding function E from Bm to Bn, we need to find an Nm decoding function D from Bn to Bm associated with E. Now see what is the algorithm to find that decoding function associated with given encoding function. Since Bm has 2 raised to m elements, there are 2 raised to m code words in Bn. Now step 1. List the code words in a fixed order. x1, x2, x3, x2 raised to m because these are 2 raised to m in number. Step 2. If the received word is xt, we compute distance delta xi xt for 1 less than or equal to I less than or equal to 2 raised to m and choose the first code word from the list, say xs, such that minimum of delta xi xt is equal to delta xs xt. That is, xs is the code word largest to closest to xt and the first in the list. Now see, the first step is first we have to arrange all the code words in a fixed order, say x1, x2, x2 raised to m. Now suppose the received word is xt. Now for xt, keeping it fixed, we find all the distances. That is, we find delta x1 xt, delta x2 xt and delta x2 raised to m xt. So we find all these distances. Then we have to select the first code word from the list, say xs, such that distance between xs and xt is minimum among all these distances. That is, xs is the code word closest to xt and first in the list. Now step 3. If xs equal to e of b, we define the maximum likelihood decoding function d associated with e by d of xt is equal to b. Note that D depends upon the particular order of code words in E of Bm. That is, if the code words are listed in a different order, we obtain a different maximum likelihood decoding function D associated with E. Now one more theorem. Suppose that E is an Mn encoding function and D is a maximum likelihood decoding function associated with E. Then ED can correct k or fewer errors if and only if the minimum distance of E is at least 2k plus 1. So here this theorem gives us how many errors ED can correct, and it depends on the minimum distance of that encoding function E. If it is at least 2k plus 1, then ED can correct k or fewer errors. Now, these two are important results. Let E be an MN encoding function and D be an NM decoding function associated with E. The following two statements regarding detecting and correcting errors are very useful in problem solving. First, a code ED can detect k or fewer errors if and only if the minimum distance of any two distinct code words is at least k plus 1. Means minimum distance is at least k plus 1. Second, a code ED can correct k or fewer errors if and only if the minimum distance is at least 2k plus 1. Now, one more theorem. If H is a finite subgroup of a group G, then every left coset of H in G has exactly as many elements as H. Now see example. If E is 2, 5 encoding function with minimum distance 3, then how many errors can this code detect? How many errors can it correct? Now here we will use the result just we have seen. An MN encoding function E Bm to Bn can detect k or fewer errors if and only if its minimum distance is at least k plus 1. Now here minimum distance is given as 3. So it is at least k plus 1 means 3 greater than or equal to k plus 1. It means k plus 1 less than or equal to 3. So k less than or equal to 2. The code E will detect 2 or fewer errors. Now, E can correct k or fewer errors if and only if minimum distance is at least 2k plus 1. Now, the minimum distance is given as 3. So, 3 is at least 2k plus 1 means 3 greater than or equal to 2k plus 1. So, solving we get 2k plus 1 less than or equal to 3. That is 2k less than or equal to 2. So, k less than or equal to 1. So, the code will correct 1 or fewer errors. Now next example, show that 2,5 encoding function E from B2 to B5 defined by E of 00 is 5 times 0, E of 01 is 0 triple 1 0, E of 10 is 10101, E of 11 is 11011 is a group code. Consider this group code and decode the word 4 times 10 relative to maximum likelihood decoding function. Now first we have to show that E is a group code. That is, we have to show that the set of code words C equal to E of B2 is a subgroup of B5. Now to show that it is a subgroup of 5, we check for identity element and closure property. Now the identity element of B5 is 0005 times, which is member of C as it is a code word. Now to check the closure property, we prepare the composition table for all elements of C. Now after preparing the table, it is observed that the operation ring sum is closed in C and C is a subgroup of B5. So we can say that E is a group code. Now we list all the code words in some specific order. Let x1 is equal to 005 times, then x2 is 01110, x3 equal to 10101, and x4 is 11011. Now we consider received word xt as given 11110. Now we calculate distance between x1 xt, then x2 xt, x3 xt, and x4 xt, which we have written as delta xi xt for 1 less than or equal to I less than or equal to 4. Now, what is distance between two words? It is nothing but weight of x ring sum y, that is delta xy. So, to find delta x1 xt, distance between x1 xt, it is weight of x1 ring sum xt. So, you can add them x1 with xt. So, it is equal to 4 times 1 0. So its weight is 4 as there are 4 ones. Similarly, distance between x2 xt is equal to weight of x2 ring sum xt. So again adding them we get 1 4 times 0. So it contains only 1 1. So it is 1. So in this way after calculating all the distances, see what is the minimum distance. So minimum distance is 1 and it is for x2. So in that algorithm that xs is x2 here. So minimum of delta xi xt is nothing but delta x2 xt. Now what is x2? It is 0 triple 1 0. Hence we now choose the code word which is closest to xt. Here x2 is closest to xt. So maximum likelihood decoding function d of xt is equal to 0 1 because it is given that e of 0 1 is equal to 0 triple 1 0. So from that as x2 is closest to xt, from this we get d of xt equal to 0 1 as maximum likelihood decoding function.